made its way to the Earth and before it was discovered. And I had also told you that normally the nomenclature is given by the Meteorological Society based on, where the rock actually fell, by whom it was discovered, the year. But the scientific basis for the classification of meteorites lies in its, chemistry, its mineralogy, right? I'd explained that to you as well. I had given you an example about this particular fall that had happened in 2008 of this small asteroid called 2008 TC Cube, right? That was discovered by a telescope in Arizona in the US, which is one of the major, planetary research centers, ASU, right? And it was tracked, and then the rock fragments were collected immediately over the Nubian Desert in northwest Africa, and it exploded about 40 kilometers, above the surface of the Earth and fell over a large area. This map, the entire area that you see, that's where these rock fragments were collected by scientists as well as nomads who helped them collect that. And here at the bottom, you can see some backscattered electron images when the rocks were collected. Right, we normally cut them off, we polish them, then we put them under the electron microscope, right, bombard them with electron beams to actually analyze, what is the chemical makeup, what kind of minerals are present, what kind of phases are present in these rocks. And also with the help of laser ablation, these small pits, this figure, in the bottom figure, figure D, you can see these circular, you know, shapes. So those are not natural shapes. Those are, shapes that resulted as a result of ablation from, laser with a laser beam. Because I wanted to test what kind of material is this, right? And then I had shown you the SPY diagram, which tells us that in the established meteorite collection, where do most meteorites come from? So most of them, they come from Antarctica, right? The polar regions. There are annual expeditions to Antarctica every year, right? Where any of us who's above 18 can volunteer for that. And then on the basis of a criteria, they can be chosen, right? Then the Sahara Desert, Northwest African deserts, and then from, different places, other places on the earth. Technically, they can fall anywhere, right? So a quick question to you guys again. Yes, I had explained that to you. Why is it that most of the meteorites that we find, either they come from the polar regions or from Northwest Africa? Any guesses? It's just,
Can you ask again, sir?
So if you look at this pie diagram, it shows that, by numbers, most of the meteorites that are present in our collection, right, they came from Antarctica, or they were discovered in Antarctica. The rest were discovered, in the Northwest African deserts, Sahara Desert, right? Some came from the Arabian Peninsula, some from Australia, and, rest everywhere. It's just a tiny sliver in the pie diagram. So what is the reason that, Antarctica and Sahara, most of the meteorites, in our collections, they appear to come from these regions?
Sir, it may be because there is means less or no rain or other weathering factors present in Antarctica.
Okay. Yeah, that could be one of the reasons. What else? One of the obvious reasons is that, like you said, that lack of, alteration. That is one thing. Another thing is that, let us say, if a meteorite sample, a small rock, fell over somewhere, where in a very urban area, right? Or in a very normal area where there's already a lot of, dust, lot of, rock fragments scattered. So it's very difficult to distinguish that, right? Unless it is observed and it makes some damage or people observe it to be falling, right? Other than that, it becomes difficult to distinguish it from the surroundings. Whereas in the polar ices, right, with the snow and the glacier background, it's very easy to distinguish the rock samples that have fallen, the meteorites that have fallen from the background. And the same is the case with the Sahara Desert, right? And so that is one of the reasons. that it's much more easy to, you know, distinguish them from the terrestrial materials and collect them immediately. And same is the case with the micrometeorites also, right? For all technical reasons, even here at in IIT Roorkee, let us say if we set up a collection trap right on top of a building, so a lot of dust particles will fall in, including micrometeorites, cosmic spherules. But at the same time, their proportion compared to the normal terrestrial dust would be very small and will be very difficult to distinguish. And in contrast, we had set up, you know, a collection trap in Leh and in Ladakh. So it was much more easy to collect it over there because, you know, atmospheric pollution was low and it was easy to distinguish those micron-sized particles from the terrestrial dust. So that is one of the reasons why we find, you know, most of these meteorites. It's easy to discover them from the polar regions as well as in the Northwest African deserts. And here is an example that, you know, just like we are speaking of meteorites, we defined it in the context of the Earth, right? So one can ask that at some point in its history, you know, the Earth was also undergoing collisions. It is very much feasible that some broken fragments of the Earth, they would have traveled to other planetary bodies, right? So what was discovered recently was that there are meteorites that are found on the surface of other planets as well. For example, this picture on the right-hand side is the image of a meteorite that was found on Mars. And Mars is one of the most well-studied planetary bodies apart from the Earth and the Earth's moon, right? And it's continuously being monitored. So it was easy to discover that, you know, this rock wasn't present over there. And then during the next orbit of this spacecraft, it was found that this particular rock was found to be present over there. So it's probably a meteorite from another planetary body that, you know, reached the surface of Mars. Right, then easy peasy, I had shown you this classification, why it's actually important, you know, to investigate these meteorites and what do they actually represent. And I had shown you this, you know, cartoon starting from the initial material that was present in the solar nebula, right, to a full-fledged differentiated or layered planet, right? You look at the top panel of figures, right? So with the crust mantle core layers and different meteorites that we find, they appear to be perfect analogs for these hidden reservoirs, right, of these differentiated planets. For example, iron meteorites, right, they can be treated as analogs for the metallic core of the planetary bodies. Stony iron meteorites, which are a mixture of, you know, metal and silicate phases, they can be representative of a mixture of core and crust or core and mantle material, right? Then we have the silicate or the stony meteorites that are representative of the rocky portion of a planetary body, right? Portions that are made up of silicate minerals, right? And most importantly, the first one, if you look at the, you know, first figure over here in the cartoon, both top and bottom, meteorites that are most pristine and are representative of some of the oldest material found, you know, in the meteorite collection, right? They can be treated as analogs for the building blocks of the planets. Okay. And a simple classification based on, you know, their mineralogy, what kind of material is present. They can be divided into stony meteorites made up of, you know, rocky material, largely of silicate minerals, iron meteorites, metallic iron nickel alloys, right, together with minor components of iron sulfide, silicide, carbides, reduced phases, right, and then mixtures of, you know, iron and silicate minerals, which are the stony iron meteorites. Okay, and then we had discussed about this that it's also important to distinguish, you know, meteorites from parent bodies that were primitive and undifferentiated, as in, you know, bodies that formed but did not go, you know, separation into these different metal and rocky layers, right? And in contrast to those bodies that underwent large-scale melting, were a core component that separated out from the rocky material, right? And so that is another way to classify meteorites into primitive and undifferentiated, and meteorites that come from differentiated planetary bodies. For example, in this picture cartoon over here, right? So the first one that can be treated, the one that is representative of, you know, oldest material, most pristine material in the solar system can be treated as coming from an undifferentiated body, right? That means that the kind of material that was being incorporated into growing planets, somehow this material escaped that processing, and that provides us information about that kind of material. Whereas the rest of the meteorites, the stony irons, the irons, as well as the ones that are coming from the crustal part of other planetary bodies, they come from a differentiated planetary body, right? So now let's go back. We had discussed about, comets, asteroids, and meteorites. So what are the relations between these, different rocks or different materials that are found in the solar system? So, major difference lies in terms of their composition, especially between comets and, asteroids. That ice or volatiles, I've simplified it here in the form of ice versus rock and metal, right? So comets, if you remember, they consist of largely of volatile materials, icy materials, right? In contrast to asteroids and meteorites, which consist of rocky and metallic material. Their orbital characteristics, random inclinations for the comets versus low inclination for the asteroid belt. The region of origin. Remember, the comets originated. There are two main sources of comets in the solar system, which are the Oort cloud and the Kuiper's belt, right? Versus the asteroid belt, which is the origin of most of the meteorites, right? And very importantly, whether these objects they show cometary activity when approaching the sun, basically losing out on the volatiles, right? About the material, please don't worry, try to listen and grasp something in the class. I'll share all the material with you, so no worries about that. But please try to participate and listen carefully, right? So now a question that you should be asking, right, after all this discussion is that, can a comet ever become an asteroid, or can an asteroid become a comet, right? And if you remember, we had discussed some cases. So according to the International Astronomical Union definition, once a comet has shown cometary activity, it is a comet, and then it cannot then become an asteroid. But then there is a caveat over there, is that, let's say, if it loses out on all its volatiles, so it's not going to show any cometary activity. So can we not say then, right? Or let us say there was a comet way back, right? It lost out on all its volatile, and by the time it was observed, right, it basically consisted of loosely consolidated, rocky materials. So can that not be mistakenly classified as an asteroid? So, this definition that seems to exclude the possibility, like I said, of a comet losing out all its, dust and ice volatiles, and maybe it becomes extinct completely, or it consists of, the last remaining refractory material. So at that point, it would more or less appear like an asteroid. So there was a paper by Huish and Jewett where they treated a few main belt asteroids, and they found that they exhibit comet-like characteristics. Right, there are some volatile rich materials found in the asteroid belt, and they contain a lot of volatiles in them. So they thought that not only can comets become, after losing their volatiles, appear like asteroids, but some asteroids, they could be volatile rich, and they are seen to be giving out, or emitting volatiles, especially when they're at their point of closest approach to the sun. So there are some exceptions. So there are 5 objects basically, right? So if you see, here is a picture of 2060 Chiron, right? So there are several objects that have been cross-listed as both comets and asteroids, and they are being studied in great detail, investigated, that where can we draw a line and slot them in either of these categories. So like I said, it's 2060 Chiron, 4015 Wilson Harrington. You didn't have to memorize this. This is just to, those of you who are interested, you can actually Google the name of these objects and then see, okay, there's 118401 linear. So there are several of these objects that have been plotted as both comets and asteroids. And there are several parameters on the basis of which we can distinguish between these. But one common method which can be used to distinguish between comets and asteroids is known as the Tisserand parameter, right? I'll give you some brief details over here, and those of you who are interested, you can visit this, web address for more detail. And I can also, provide you a review paper if you're interested. But let us see what is the Tisserand parameter and how is it used to distinguish between comets and asteroids. Okay. So it's the Tisserand parameter is just, based on a very simple, n-body problem that we deal with in classical mechanics, right? Where there are n number of bodies that are present and how they are, going to impact each other if we know their positions, right? Their masses and their velocities. So how the entire system is going to behave. And three-body problem is a simplified case of that, and we apply it to our solar system. The sun being the most massive object, then Jupiter being the second most massive object, right? And a third object, which is either an asteroid or a comet, that can be treated as a third object. And the Tisserand parameter is calculated with respect to Jupiter. Okay. So Jupiter is the most massive planet in the solar system and exerts the greatest dynamical influence, right, on comets and asteroids. For this reason, the most commonly seen Tisserand parameter is the one that is calculated with respect to Jupiter, and we denote it as Tj. J is the subscript over here, right? So here is the definition of the Tisserand parameter with respect to Jupiter. That could also be calculated with respect to any other body, but Jupiter, like I said, being the most massive planet in the solar system and present just outside the asteroid belt, defining, the periphery of the inner planets and the outer planets. So we calculate it with respect to that. And here's the mathematical expression for calculating the Tisserand parameter, right, which contains, terms for the semi-major axis of Jupiter, semi-major axis, the eccentricity, the orbital eccentricity, right, of the object, the orbital inclination of the object. The orbital eccentricity basically defines whether the orbit is circular, how much it deviates from a perfect circle. Okay, so this relationship here that basically relates the semi-major axis, the eccentricity, the orbital eccentricity, and the inclination of the object of any solar system object, relating it to the semi-major axis of Jupiter, right? And strictly speaking, this Tj value, like I said, this Tisserand parameter could have been calculated with respect to Saturn or even the Earth, but normally calculated with respect to Jupiter. Okay, and if the value is found to exceed 3, it is found that for most of the asteroid that fits. So for asteroids, the Tisserand parameter, which is calculated with respect to Jupiter, that has a value exceeding 3. And if the value lies between 2 and 3, right, so those are basically comets. Okay, so that is an additional parameter that is used to distinguish between whether an object is a comet or an asteroid. So for one of the tutorials, I'm designing, some problems with respect to this. I'll share with you, I think, in a couple of days. And if you're interested, you can go to this website over here and you'll find much more details about this Tisserand parameter. Okay. So let's talk about the centaurs. Hello? Am I audible to you all?
Yes, sir.
Okay. Okay. Were the slides not moving earlier? I just thought.
They were moving, sir.
Okay. Okay. So let's talk about the centaurs, right? So the centaurs, they are a class of minor planets, okay, that have characteristics that are half asteroid and half comets. So here in this figure on the right hand side, you can see, there's the sun at the center of this figure. Then the blue dots, those are the giant planets, Jupiter, Saturn, Uranus, Neptune, right? And the Kuiper belt objects are shown in with these green symbols over there. And scattered within these, you can see these orange dots all over. So those are the centaurs. which are termed as minor planets, okay, and have the characteristics that are half asteroid and half comets. And like I said, Chiron was the first body that was discovered that belonged to this population way back in almost more than 40 years back. These are basically icy bodies that have unstable orbits within the orbits of the outer planets. Several of these, they have their orbits within the orbits of the outer planets and mostly lie inside the Kuiper's belt. If you see all these orange symbols, they are scattered, between the Kuiper's belt and even between the orbit of the giant planets. Okay. So they have characteristics very rich in volatiles, but they also contain, these massive iron and metallic as well as rocky materials. So let's see, there are several other objects which are termed as the scattered disk objects. They are a type of trans-Neptunian objects, right, with high orbital eccentricities, almost up to 0.8, high inclinations up to about 40 degrees, and their points of closest approaches to the sun normally exceed 30 astronomical units. So the basis of modeling and calculations, it has been suggested that such orbits, they result from gravitational scattering by the gas giant planets and further interactions with Neptune. And the range where these objects can be found, they can extend well over 100 astronomical units from the sun. And the inner region of the scattered disk, they overlap with the Kuiper's belt. And there are several short period comets, the Centaur objects, many Oort cloud objects. They are believed to originate from this scattered disk. Okay. So one of the main objects that is found in the scattered disk, among the scattered disk objects, is Eris. Okay, it's typically, this is made up of water ice or frozen methane, and the objects within the disk are quite tiny. Eris is one of the largest objects that are found among the scattered disk objects, and which has sufficiently large dimensions to classify it as a dwarf planet. Okay, so you can note it down. This can be one of the topics for a micro presentation, that how are dwarf planets defined and what are the characteristics that distinguish them from, defining them as a full-fledged planet. So that could be one of the topics for a micro presentation. But here what I wanted to show you is that these objects that are found among the scattered disk objects, again, they hold very important information because they're very rich in volatiles, right? And several of them are believed that it could be that the subsurface, right, the surface is frozen, but the subsurface, that would be briny or slight, even liquid water, or can be present over there, which is conducive towards, the existence of microorganisms. We don't know yet, but on the basis of modeling, it has been suggested. And we'll treat, several other examples as we move on further. Several of the satellites of the gas giants and the ice giants, right? It is believed that they could be containing, microorganisms, or at least the conditions are conducive, right? So, in practice, many of the meteors, which enter the Earth's atmosphere, they break up and are completely, destroyed during their entry into the Earth's atmosphere because of frictional heating. By the time, they would have reached the surface, almost the entire bodies, they get, volatilized, completely burnt out. But there are several that survive their passage, and that is how we find the meteorites. So technically, it is possible for both comets and asteroids to impact the Earth, right? Or for that purpose, any other solar system body, and fragments of both kinds of bodies can, in theory, become a meteor. Okay, so what distinguishes that, what kind of material actually survives and we can find access to, this basically a function of the intrinsic properties of the material from which the asteroid or the comet is made, whether it's very friable, it can break off, or it's very consolidated, high density material, right? Depleted or in volatiles or enriched in volatiles. So that is what determines whether it will survive its passage through the Earth's atmosphere. And clearly, the stronger one, less friable one, less breakable ones are more likely to survive the transit through atmosphere. Almost a decade back, it was reported in parts of Gujarat, that big, icy fragment was discovered, and immediately it was bagged, and people thought that it could actually represent, be representative of a comet. But later on, it was analyzed. It was found that it was just some terrestrial material, right? There was no cometary, geochemical aspects or isotopic characteristics, and it was clearly established. But then, if at all it is possible to collect such material, that would be very valuable towards our understanding of the early solar system. So the likelihood of material that derived from an icy comet reaching the surface of the Earth is, very, very less compared to material that, let's say, comes out from an iron nickel asteroid. And are you aware of any, asteroid that is made up of largely metal or iron nickel metal? Because normally asteroids are rocky bodies, but there are, some asteroids that have been, the center of attention for the last couple of years, many years. For example, asteroid Psyche, right? It was found that it is made up of almost completely iron nickel metal and could be a big reservoir for the platinum group of elements. So here the point that I was trying to make is that it's very, less feasible for a fragment from an icy comet to reach and survive, the surface of the Earth, compared to material coming from a rocky body or an iron, nickel, or a metallic body. So if material from comets has arrived at the surface of the Earth, it's possibly again very difficult to recognize, and maybe it's more difficult to actually find and collect. And before that, possibly it will completely volatilize. So nevertheless, we do have some examples of cometary materials that are there in our meteorite collections. There was this paper by Gunnell et al. Almost 15 years back that suggested that the carbonaceous chondrite meteorite, or Aguil, may have a cometary origin, right? So they thought that this carbonaceous chondrite, it does contain volatiles that may have signatures of comets. And another possibility was the recent fall, or now I think a few years back, of the Tagish Lake meteorite, when it was, analyzed, especially for its isotopic characteristics and the kind of material that it was made up of. It is debated whether it actually represents, a broken fragment of an asteroid, or it could contain cometary material in it. So the Tagish Lake meteorite, let's consider the case study of that. It was basically a 150-ton space rock that plunged into the Earth's atmosphere way back in 2000. And here's a close-up of the Tagish Lake meteorite on the right-hand side. And as you can see, all these cracks, and also was made up of very fragile and very friable kind of material, right? Very porous material. Okay, so it was found to be, approaching Northern America, parts of Northern America, and as it approached the Canadian, very remote territories, further than almost near Alaska, this meteor that traveled at the speed of a very fast highway car, let's say about 170 miles per hour, is traveling with that kind of velocity. And a big team of scientists, the entire scientific consortium, consisting of several US universities and NASA, they initially tried to uncover the debris, the material that fell over the Canadian remote territories, and immediately those were sampled, right, collected into bags very quickly and taken to the laboratories. And even some of the gas bubbles that were contained within these rocks, they were analyzed for their isotopic characteristics. Okay, so this meteor that had finally exploded with the energy of 2 to 3 kilotons of TNT. You know what is TNT?
Basically, bomb material.
Yes, dynamite or bomb material, right? So it exploded with the energy of 2 to 3 kilotons of TNT, right? And when we'll be doing the impact cratering processes, we'll study about, these collisions or these in more detail, that when a body actually bombards or collides with the Earth, what happens. But this was the, effect of this meteor exploding the Earth. So since the rocks had never reached extremely high temperatures, right? So the frozen gases that were present within these fragments, they could not volatilize or boil off. So it was possible for scientists to actually study them, right, and understand that what kind of volatile materials was present inside these rocks or the parent bodies of this rock. So it was described as porous ice, like sampling on the surface of a comet, and these were the most fragile meteorites ever discovered. So this was the reason why it's highly debated whether it may be having a cometary origin or not. And it represents, a member among our meteorite, collection consisting of such kind of material. And basically, the geochemical analysis, the isotopic analysis has shared, has given us extremely important information about the kind of material that was present, between the outer and the inner planets. Okay. So another question that, we should be asking is that we had been discussing about the asteroid belt, possibility of, confusing between comets and asteroids. But we should ask that, do all the meteorites, they come from near-Earth asteroids? If you remember, we had dealt with the Kirkwood gaps, right? So there are some gaps if we plot the distance from the sun and, the amount of material that are present in the asteroid belt. So that bears a certain relationship with the distance from the sun. And at certain distances, they are completely devoid or depleted in material. And we believe that's the origin of these near-Earth asteroids. So we can assume that most of the meteorites, they come from the near-Earth asteroids, since these are the most abundant asteroids that have Earth-crossing orbits. But how can this be validated? So basically, this entire hypothesis could be validated by analyzing the compositions, right, together with a range of, other constraints that we have. And a study by Vanaza et al. That showed that most of the near-Earth asteroids, they have actually got a very specific composition, a certain kind of meteorite known as the LL ordinary chondrite, which is actually a very uncommon variety of meteorite. Only about 8% of the meteorite falls, are of this type. So it was established that meteorites actually come from the main asteroid belt rather than just originating from the near-Earth asteroids, right? And they are representative, their compositions are representative of, of an entire range of compositions ranging from very volatile material to very refractory material. Okay. And here are some more details that I would like to show. If you look at this picture on the top left-hand side, right? So that's an Antarctic meteorite, right? Showing a particular, feature known as the Regmablyps, right? If you see, it appears as if, this entire rock, especially the outer surface, it was pressed, and, these dent kind of features that you can see over here, as well as on the left hand side. So what happens that, much of the mass of the meteoroids that I mentioned that entering the Earth atmosphere, they completely get ablated, destroyed, right, during ablation. Larger meteoroids, more than 10 centimeter, typically have survival fractions where only about, from 1% to about a quarter or 25% of their initial mass that survives, right? What happens to the remaining ablated material, it's unclear, but we do think that it may recondense through, coagulation as micron or nano size particles known as meteoritic dust. Okay, but the larger fragments that survive, once they get ablated during their, flight within the Earth's atmosphere towards the surface, their outer parts get molten sometimes. And because of the frictional drag or by the atmospheric drag, the outer molten portion can also get removed sometimes. So many of these meteorites, they show a kind of fusion crust. Okay, so let's say, for example, this large object, if we break it up, right, and if we are able to see a cross section, what we'll realize that it consists of an outer layer, which is made up of this fusion crust, right? And that is where these features called the Regmablyps, right? They are basically thumbprint-like impressions that are caused by ablations, they form. Okay. So observations, they indicate that the interior of the meteorite, normally they are not strongly heated because of the ablation of the exterior. So if you remember, there was a big disaster that had happened with the Colombian space shuttle way back that also had one of the Indian origin scientists in it, Kalpana Chawla. What had happened is that when it was trying to re-enter the Earth's atmosphere, one of the outer tiles that had fallen off. So the outer tiles, they are made up of very refractory material. So what happens that in these objects is that the outer tiles, they get heated, but they contain all the heat and keep the inside insulated. Okay, the heat doesn't travel inside, but in the case of that spacecraft, one of the outer tiles had fallen off. So which basically completely heated up the interior and everyone died. And the big tragedy disaster that happened with the Colombian space shuttle. So similar to that, in these meteorites, the outer portion is made normally, the refractory material that gets ablated and forms like an insulating material. So the inside, they are normally not strongly heated because of the ablation of the exterior. But that leads to the formation of these regmaplets or these thumbprint-like impressions. Right. So let's talk about links between comets and meteor showers, right? So we have, many of us have seen, something for like the, meteor showers or these falling stars, those kind of things. So what happens is that flurries of meteors that seem to emerge from, points in the sky at many times of the year, we term them as meteor showers. And normally they are very well covered these days, with the internet, they are very well covered in the media. Sometimes you can find live updates. Okay. And they are produced by small fragments of cosmic debris, leftover materials, right? Dust particles that enter the Earth's atmosphere at extremely high speed. So they get ablated or burnt out. That's why we see the bright.
You are not audible, sir.
Is my voice okay now?
Okay, sir. Okay now.
Okay. Okay. So I was just giving you, this example about these, flurries of meteors that seem to emerge from, parts of the sky. And basically, these are cosmic debris or planetary leftover material, dust particles that enters the Earth's atmosphere, gets ablated, burnt up, right, emitting light. And that is what we see during these meteor showers, right? So what happens that,
Excuse me, sir.
yes, please.
Sir, have you seen any meteor shower?
I have seen live updates of meteor showers, right? Because sometimes, you start to get these updates that, this is going to happen. And it does happen in several places. So you can see live updates if you, search for it. And there are several videos also. So that can be seen. And with, telescopes and all, even close resolution images of that you can actually see. And
Okay,
sometimes,
sir.
of like a single object getting burned up, where it's in popular culture, they call it a falling star. Okay. So that's basically one of the larger objects entering, getting burned up. So it's not a falling star, but just a piece of, extraterrestrial material entering the Earth's atmosphere, getting burned up. But sometimes very small fragments, right? They cross the Earth's object, right? And then when they are entering the Earth's atmosphere, it appears as if the entire flurry of material is entering and getting ablated, getting burned up, and that is what we call as a meteor shower. And the larger among them, they may actually survive their passage and can be discovered as meteorites. So if you remember a couple of slides back, I showed you that just about 1% to a quarter of the material that is entering the Earth's atmosphere that survives. The rest gets completely ablated. Okay. So meteor showers can result from a variety of materials, right? So many a time, or a comet that swings by the sun, it produces large amounts of dust particles, which will eventually spread out along the entire object, orbit of the comet to form a meteoroid stream. If you remember when I was telling you about the classification, we looked at the term meteoroid, meteorite, and meteor, right? So when it ends with a D, right, it's different. That means it hasn't entered the Earth's atmosphere. It hasn't survived its passage through the Earth's atmosphere. right? When a meteoroid that enters the Earth's atmosphere survives and we discover it, then only we call it a meteorite, right? Otherwise, these objects are basically meteoroid. And if a comet is moving around the sun, right, so it's basically degassing, leaving out a trail of material, basically filling up the entire orbit to form a meteoroid stream. And if there's an overlap between the Earth's orbit and the comet's orbit, right, basically if they are intersecting at some point, then the Earth will pass through this stream for a few days at roughly about the same time, each year, producing a meteor shower. So if you look at this cartoon on the right hand side, right here we have the Earth's orbit in green, right, and we have the comets or the stream of the material left over by the comet in this pink and orange color, and it intersects the Earth's orbit twice, right? So it's basically like, intersecting disks. Here we have these intersecting objects. So as the Earth is moving, it's going to encounter this material twice during its orbit around the sun. Okay, and that's how we at times at regular intervals, right, or at fixed times of the year, we do encounter these, meteor showers. And there's a very nice, interactive comet animation. If you go to this website, I'll share the material with you. You can click on that and you can actually see what happens. They have, made this animation. It's quite cool. So you should check that out. Okay. So what I will do is that I'm going to stop over here, and I wanted to talk to you all about, your tutorials as well as about the class participation. So last time we had a class assignment, right? Several of you participated and you sent over the completed assignment to me, and I'd promised that last time we are not going to, use it for your grading, right? But here what we are doing, we are progressing, from topic to topic. We are moving ahead with the lectures.